So let me thank the organizers for the invitation. Please ask questions. I will repeat the questions. I want to discuss a somewhat exploratory idea, which is the one of trying to relax the cosmological constant. By this, I mean the possibility of explaining the smallness of the cosmological constant or dark energy by some sort of historical mechanism, meaning that the cosmological evolution drives you to these small values. Okay? And it's a work with these collaborators, and I will probably not have time to talk about this, and some work in progress. Motivations. Well, I guess maybe this is not the right audience, but I think it's I think most people think that the acceleration of the universe is just due to a cosmological constant, and somebody thinks that this is probably okay in the sense that through the anthropic selection, maybe the problem of why the cosmological constant is so small is not very well posed. Well, this as a danger, and quoting Savas Dimopoulos, that this kind of anthropic explanation, they have the danger of premature application, meaning that it's just a way to give up, and okay, accepting that it's a small value, so this is clearly a danger, and I think it's worthwhile trying to address the problem. And another reason is, which is very important for this audience, is that if you think about it, the only reason why we are talking about dark energy and modified gravity, the only reason, I think, is because of the cosmological constant problem. In the sense that I think that if the cosmological constant was like the mass of the electron, was a small number protected by a symmetry, I don't think anybody would go. I mean, maybe somebody might, okay, but most of the research in this area is driven by the fact that the cosmological constant is small. On the other hand, unfortunately, 99.9% of the models we talk about have nothing to do with the solution of the cosmological constant problem. Usually they are at least as fine-tuned as the cosmological constant, if not more, because maybe there are other fields that you have to protect and so on and so forth. So this is a disclaimer. So I think it's important to try to do something. At least I would try to have a model of dark energy, if you want, that has something to do with the cosmological constant problem. It will be a model, or I mean, a class of models in which the good thing is that you are left with some light state, meaning it's not something which, like the landscape, in which at the end the phenomenology is the one of a small cosmological constant. So at least, although it will be very model dependent, you are left with some light degree of freedom that knows about this mechanism. As I will explain, it requires the violation of a null energy condition, and this looks quite general, which I think it's important because it may be that, I don't really know, but it could be that NEC violation is something which is theoretically ruled out for reasons that we don't know it, but it's something that motivates also to look for this question, because if you can rule it out, then all these ideas are just gone. Okay, so of course you need all these motivations in this slide, because as it will become apparent, the implementation is really not compelling. Okay, so you will apologize for this. Okay, so let's start. So the idea is not new. I mean, somebody already, of course, thought about it. The first paper was by Abbott many years ago. And the idea is very simple. So you can have a potential, like a washboard potential, with many, many minima. This not looks completely crazy, because it's enough to have some sort of sinusoidal potential, given, for example, from some non-perturbative effect. plus a tilt, a linear tilt, okay? And notice that, okay, there is no problem in having a potential like this in the following sense. All these parameters can be naturally making small, okay? So from this point of view, having small barriers or a small tilt is completely fine, in the sense that it's at least technically natural. And the idea is very simple. There are all these minima, and what happens dynamically? Well, dynamically, if I start here on up on the washboard, at the beginning, quantum fluctuations due to the seater temperature will make you jump from one minimum to the other. Actually, the minima will not even be there for sufficiently high h. And at a certain point, I will get stuck in some of these minima. And if the potential, if I choose these parameters, the potential where the minimum where I get stuck in correspond to a small cosmological constant, maybe the one that we observe today. Of course, there are two giant, enormous problems, well, especially the first one. Well, the first one is that by the time I get here, and this was already pointed out by Abbott, by the time I get here, the universe is completely empty, because, of course, everything redshifts, and basically, you are left with a small cosmological constant and nothing else. So there is no standard cosmology, okay? So it's an empty universe, okay? And if you think about it, this looks quite general, because it just follows from the following. If you want a mechanism which relaxes the cosmological constant, you must be sensitive to a small cosmological constant. So you must distinguish a small cosmological constant. And if, of course, if the universe is very energetic, the small cosmological constant, given that it has only gravitational effect, will be swamped by all the rest of matter and radiation. Okay, so it looks quite general that people, for example, another possibility is that you think about this global modification, in the sense that basically you have some non-local or global mechanism for which, for some reason, you are sensitive to the whole history of the universe. Okay, but you have to do something. Otherwise, of course, when the universe is very energetic, there is no way to select dynamically a super tiny value compared to those energy scales. So that's why what we have to do is to resurrect the universe, meaning having a mechanism like this at low energy, and then recreate the universe again, in a sense going up in energy. And this requires the violation of a null energy condition, as already pointed out by other people. Okay, this is one problem. The second problem is that, well, this is not so different from a landscape, in a sense that this model has eternal inflation. So you're going to populate a lot of vacua, and you are going to start again discussing what is more likely, where you want to live, and so on. Just to make it concrete, Steinheck and Turok and Abbott, they both chose a potential like this, but they reached completely different conclusions, because Abbott thought that you are going to live in the first minimum, which is stable enough to allow for a cosmological, for a size, for a normal cosmological evolution. While Steinheck and Turok, for some, taking into account the measure and the volume and so on, they said that you are going to live in the last positive energy minimum, okay, because it's the one that dominates the volume. Okay, but this is just to say that this gives completely different answers, because of course you have to choose. So we want to get rid of this problem. Okay, so a nice picture to illustrate the idea, and then the model will come. So the idea in principle is simple, and so you have a relaxation. Think about this, I will enter into details, but think about this as, for example, a very shallow potential, which slowly diminishes the cosmological, the vacuum energy, okay, like some sort of slow inflation. And the cosmological constant will start with the high value corresponding to some h star. Okay. As we will see, we are not able to relax an arbitrarily large cosmological constant. With the models that we found, we can relax something up to a TV scale, TV to the fourth, okay, which is would be already good enough. Okay, but so just to tell you the rules of the game. The rules of the game are that you have to make a model and some sort of Lagrangian, and if somebody comes and changes the cosmological constant without telling you by a certain amount up to this TV to the fourth, the model automatically should relax to the same small value of the cosmological constant. Okay? So it might be insensitive to unknown changes that in the CC. Okay, so you have a period in which the universe relaxes and the cosmological constant becomes very small. I say cosmological constant, but of course is a dynamical dark energy, until a value which is probably comparable to the one we observed today. And then once H becomes small enough, there must be some sort of phase transition, and I will explain in what kind of phase transition. And after this, something else must go on. There must be, as I said, the violation of a null energy condition, a rise in the energy density. And after this, you will have inflation and reheating and the standard cosmology. Another point that I want to make from the start is the following. Of course, you can say, okay, but come on, if you're going to relax the vacuum energy early on, how do you know that eventually, when you do all your stuff, and eventually you have reheating, phase transition, and so on, how do you know that the observed vacuum energy is the same we relax early on? Of course, it's not the same vacuum, but you can impose that it is related by a symmetry to this vacuum. Okay, so it's crucial that so we early on we relax and we are in a practically empty universe. Okay, so for example, the QCD is in our state, is in the broken phase, and the same for the electroweak, because we are at very low energy. So we are relaxing exactly the cosmological constant we observe today at low energy. I'm saying this just to say, for example, from the point of view of the normal evolution, it will be strange because you have all these jumps from when you have the electroweak phase transition, the QCD phase transition, and so on. But eventually, the final jump will get very close to zero. The reason is that we relaxed early on the vacuum energy, and the vacuum energy at this stage is related by symmetry to the one we observe today. Okay, so let me sketch what kind of, I mean, I hope people can do better than this, but let me tell you what we did. First of all, we have this sector, this there is a field which I will call phi 1, which is relaxing the cosmological constant. The first thing that you can do is to think about just the same as in inflation, just a linear potential, for example. And of course, you want to be in slow roll, and you want this field to slow roll also for Hubble over the present Hubble in such a way that it scans also values of the cosmological constant similar to the one we observe. But as I said, we also want to avoid eternal inflation. And to avoid eternal inflation, you need classical dynamics to dominate over quantum perturbations, and this gives this bound. So it turns out that this is not very good. So the maximum lambda you can relax is over the 10 MeV to the fourth, which is not so good. You can try to modify the potential, and you will see that this does not work. So it's not this bound is not a consequence of a linear potential, but it's very general in this context. The reason is basically that you can have another shape of the potential, but as I told you, if somebody comes and changes the value of the cosmological constant, the model must adjust itself, and this does not work unless, again, you have to satisfy these bounds. So these four standard inflation models, but we know that there are more sophisticated or complicated models of inflation, like ghost inflation, Galilean inflations. Why these are better? Because, as we know, they have a smooth limit for lambda going to 0, in a sense that in the limit of a very shallow potential, or even a completely flat potential, these models are still going, are still evolving. Okay? So you don't have this problem of getting into eternal inflation when lambda becomes too small. You see that there is this tension which is not there in these models. For example, let me focus on this ghost model. So what is the idea? The idea is quite simple. Imagine that you have a P of x, where x is d phi squared, and you have some function. So ghost condensation just corresponds to the theory describing small perturbations around a minimum of this function P of x. Okay? From the point of view of the effective theory Filippo was describing last week, it corresponds to operators of the form delta n squared and delta k squared. Okay? To turn on these operators from the effective theory point of view. What is good is that quantum perturbations are, I mean, is the calculation of the power spectrum. And what is good is that you see that lambda does not appear. So I can scan the vacuum energy very slowly, and provided this remains small, I don't enter eternal inflation. So there is a bound. I mean, I cannot go arbitrarily high, but there are other things which are more relevant in a sense. So I cannot. All right, so at this point, we have a model like this, which slowly scans the cosmological constant, okay? But at a certain point, something must happen. And actually, one nice thing is that it's not a choice. Something happens, and the reason is the following. So the field gets stuck in a minimum of this kinetic function. You can check that the cosmological evolution brings you back to this minimum in the absence of the potential. Now we put a small tilt in the potential, and this small tilt pushes this to a slightly higher value, okay? Because it wants to accelerate. This is basically the velocity squared, okay? So you are slightly pushed out of this minimum. And the amount is just given by the usual slow roll formula. So phi dot, I mean, the perturbation in the velocity is the tilt of the potential over h. So you see that why you are sensitive to the cosmological constant. You are not sensitive to the cosmological constant, but you are sensitive to the Hubble friction. Okay? So as I go to smaller and smaller values, the Hubble friction becomes smaller and smaller, and until this small perturbation is not small anymore, and it becomes of the same order as the unperturbed velocity. And at this point, the effective theory describing perturbations breaks down. Okay? So all the operators of this form will become relevant, and something must happen because you're changing the effective theory. Okay? So something automatically happens when this occurs. And this fixes a preferred value of the vacuum energy. So when lambda is as small as this ratio, so lambda is the tilt, m1 is the parameter entering in the Ghost condensate action. So when this happens, there is some sort of phase transition. Something must occur. Okay? Of course, as I said before, small lambda can be taken very small because this is just a breaking of a shift symmetry. So it's technically natural to take it as small as we like. So this number can be chosen to be small, and this corresponds to a small vacuum energy. So if you plug in the constraints, so this transition occurs when this happens. If you remember in Filippo's lecture, so this corresponds to when what is called C becomes of the order of this operator. This is the same as saying that you are going out of the Ghost Condensate regime. And this gives me a bound on the cosmological constant, because, of course, I scan from a very high value of the vacuum energy. But of course, if I go high enough at a certain point, Hubble becomes of the same order as the cutoff of my theory. Okay? So this gives a bound. I cannot scan something which is larger than, as I said, a TV to the fourth. Epsilon 0 is the present tilt, is the present equation of state parameters that we observe today. So I don't take it very small, so you can get up to a TV. The excursion of this field is enormous, okay, much beyond what everything. So if you are worried about this, you should be really worried, because it's a huge excursion, much Transplanckian. Okay, so this one. What about now the universe? Now at this stage, the universe has a small vacuum energy. There is some sort of phase transition, because this is unavoidable. But there is nothing else. So it's very, very low energy universe. So you have to go back and recreate energy if you want the standard cosmology. And so you want a strange thing. You want rho dot, so the time derivative of the energy density, to be positive, even if the universe is expanding. So this is counterintuitive. A cosmological constant gives rho dot equal to 0. We want something which increases. So we want rho plus p negative. And this violates this inequality. K is a null vector. This is called a null energy condition. Now, we know that it's not easy, and it's for sure not easy violating this energy condition. Usually, when you try to violate this kind of conditions, you run into instabilities. The reason is that basically these conditions are ways to say that the energy is positive in some covariant way. And of course, if the energy starts becoming non-positive, you have instabilities. It's not completely general. So first of all, let me mention a recent paper which I find interesting, which has nothing to do with what I'm going to describe. But it's, the claim is that one can have a 4-dimensional violation of a null energy condition in an extra-dimensional setup, okay, in which the only source of unconventional energy is just the Casimir energy in the extra dimensions. So I'm not, but this is an interesting direction. If this is true, it seems that all these theories I'm talking about, they could in principle be UV completed, but again, this is just something to look at. So in this talk, I just focus on 4 dimensions, and it's known that exactly the theories I was talking about, this Ghost Condensate, these Galilean theories, Hordensky, all these theories, they can violate the null energy condition. Whether, it's an open question, as I said, whether these theories in this regime, they have a UV completion or not. This is something that we have to remember. We have no clue whether these theories, they can come from a more fundamental theory. So let me for example, talk about the Ghost Condensate. So it's the same as I was talking before, but it's a different field. So I'm using the same recipe, but for recreating the universe. And here, the logic is simple. I said that you are driven to the minimum of this kinetic function if the potential is completely flat. If it is tilted downwards as before, you go in this direction. Now, if I want to recreate the universe, I will push it in the other direction, because when you are at the minimum, the stress energy tensor is the one of the cosmological constant. If you go in this direction, you are going up a potential, and you are violating this condition. Okay? So, of course, it's a long story, and you have to be careful that instabilities are under control. It can be done, but I cannot have a parametrically large violation of the neck, but I can have a tiny one if you want. Another example are Galilean theories. So this, for example, is the simplest example. This is a covariant cubic Galilean, a conformal cubic Galilean. And you can check that there are solutions in which the neck is completely violated without instabilities. Now, I'm not going to describe, I can say something at the end if I have time. I'm not going to describe how, so let me go back to the story. So now I'm talking about this field, okay? I told you that there is some sort of phase transition, which is unavoidable when the vacuum energy is small enough. But I'm not going to describe how this phase transition occurs. So in a sense, why at a certain point this phase transition leads to this violation of the neck. Okay, so so you can envisage some coupling between these two sectors, kinetic couplings. But I have to say we're not very explicit in our paper. On the other hand, provided the scales in the problem are small enough, this should not reintroduce, again, a cosmological constant problem. Okay? So I can be more precise, a bit more precise, but we didn't specify the shape of the phase transition. So now what about, so let's violate the neck. So I skip all the details, which are not very illuminating, but they are in the paper. So let me point out that there are two possibilities. One is that, so what happens to this field which is slowly evolving and scanning the vacuum energy? So a phase transition will occur. So at this point, you can either think that this field, because of this phase transition, gets stuck to some, does not evolve anymore, or, which is maybe preferable, you can think that this field still go on. Yeah.
Can you go to the previous slide? Well, about the frequencies. So you say that the scales are very low, but that means that the cutoff is low. No, next slide. So it's function T, and 2 is low. But that means that the cutoff of this action is also very low.
Yes. So we repeat. Well, it's a good question. So the question is, sorry, I have to repeat. The question is about the cutoff of these theories. Yes, these theories, they have a very low cutoff of order 10 to minus 3 electron volt. It is, I will comment what happens, but notice that it's not small compared to the H, the Hubble parameter that we need. Okay? Notice that we are only gravitationally coupled to this sector. So it's so in the usual cosmological history, if you are happy to have started nucleosynthesis, Hubble is smaller than this. Another point to take into account, if I have time, is that of course this cutoff is just in this regime. So in principle, I could even think that this cutoff changes. I will explain. There is another regime in which the theory is not described by this kind of action, and the cutoff in that stage may be higher. But it's this surely some. There are a lot of things that you have to check, and this is for sure one that you want to do all what you have to do, and you have to check that the cutoff of your theory, which is always small, allows you to describe what you're doing. I only have 5 minutes, so as I was saying, if the field gets stuck after the phase transition, then you have time, to recreate the universe. So let me be very sketchy. The details are much uglier, but so think about the Ghost Condensate field, the second one. As I told you, when the potential goes up, I violate the neck. Okay, so I increase the energy of the universe. And so I can imagine a potential like this schematically. And why it has this shape? Because it's crucial, as I said, that the final vacuum energy, so the field is moving, the final vacuum energy is related by symmetry to the one we relaxed early on in the evolution. Okay? So, and in this model, for example, is imposed by a Z2 symmetry around this line. Okay? So what you can do is to check that this field must be very small, because otherwise I have instabilities. Then I have a period basically of inflation. You also need something that I didn't talk about. I will need some sort of waterfall field, like in hybrid inflation, which gets stuck and finally reaches the universe at the end. Okay? So this is one possibility. Another possibility, this is very slow. I mean, I didn't put the numbers, but you need these to be a very slow process, and it will take a lot of Hubble times. Okay? So in this case, you can only do it when the scanning field is stuck after relaxation. Another possibility is, on the other end, to do a fast violation of the neck. Fast meaning that the field is scanning the vacuum energy. So now it reaches more or less our vacuum energy. Okay, we want to reproduce the universe in a time which is comparable to the present Hubble, not much longer, otherwise the field scans to much lower values. Okay, schematically I have in mind these kind of symmetries. So let me assume that phi 2, which is this neck violating field, is periodic. Okay, so it's like an axion. So this justifies that the vacuum energy here is the same as here, because they are identified. And there is some shift symmetry, which is broken locally in field space in this red region. Okay? So the idea is that I have a shift symmetry, it's completely violated in a certain range, and then I go back to the shift symmetric situation with the same vacuum energy as at the beginning. So now, something crazy must happen here in such a way to produce the neck. So I just flash, sorry, I skip all the details, I have 2 minutes, but so what we did is to take this sort of conformal Galilean Lagrangian with, in front of these operators, a function of the field itself. Sorry, this theta is a normalized version of phi 2. Okay? And what we did is just a proof of principle. That is to say, I choose these functions with this asymptotic behavior in such a way that I violate the neck, I raise the energy of the universe up to nucleosynthesis scale in a time not larger than Hubble today. Okay? And I just check that there are no instabilities, in the sense that perturbations around this solution are stable, are not superluminal, and the cutoff, which is another point, which may depend on this, I mean, will depend on this function, so it will be a bit field dependent, is high enough for this description to work. Okay. So these are all the details, in the sense that it's also something that was already used for other purposes in the literature, but I skip. So the idea is just reverse engineering. So I'm not saying that this is nice or natural. I'm just saying if I need to do it, I don't see any showstopper. Okay? Of course, you may say, okay, how do I know whether this function is natural or not? I don't really know, but let me just stress that this has nothing to do with the CC. Okay? In the sense whether the shape of this function is protected in some symmetry, this is another important question, but it looks some sort of naturalness issue which is not related to the CC. Okay, so you have to trust our algebra. Anyway, so this is the theory of perturbations, and we can find an action for which these kind of conditions are satisfied. Okay. Well, yes, as I said, I mean, I agree with you that the model is pretty disgusting. Well, I don't know. I mean, it is. I mean, I'm just saying that we are using the same kind of theories we have been discussing last week. So it's not that we are going in some. But of course, you need to play with these functions. So it looks not very how the universe works, but you know, very strange things happened, and so you may not. So very strange. Finally, sorry, I have to conclude. I don't want to hide. There are many issues we have to face, and I didn't say anything about reheating. In picture, and you can find formulas in the paper. In pictures, you need a field, a waterfall field chi, to get stuck to a metastable minimum, and when the field reaches this plateau again, then it goes back like a waterfall field. It's not as simple as I said. There are many issues because you have to be careful that there is no back reaction and so on and so forth. But again, we didn't see any showstopper, although again, it's a lot of massaging of Lagrangians. We are thinking, well, let me, maybe this is just for Spirakov. Okay, we are thinking about the phase transition. I didn't say anything about these phase transitions. The one that triggers the beginning of this neck violation. I think a good starting point is this paper by Ivanov and Spirakov, in which what is important on this slide is just that at least you can turn on a Ghost condensate, okay, which is what we want for this phase transition. Okay, let me skip the details because I don't have time, and moreover we didn't do much. So I just get to the conclusion. Okay, what is nice is that to describe this kind of mechanism, you have to. I mean, it's not you have to describe the whole evolution of the universe, because this happens, if it happens, I mean, much before inflation and everything. So it's not something that you can. So you really have to. You have a lot of constraints to satisfy. Okay. I stress again that this is an important problem that I still not many people are working on. So I'm almost nobody. So in many cases, neck violation is crucial to obtain what you want, and it would be very nice either to find very explicit examples beyond these effective theories I'm talking about, or to find a way to prove that something is bad in your theory. As I said at the beginning, these fields I'm talking about are still around now. So you have some sort of dark energy now in these models, which is a sort of Galilean, Ghost condensate, which I mean, of course, everything is model dependent. I don't know what is the signature of these because the couplings with matter do not enter in what I said. So, but what is nice is that at least there is some sort of dynamical evolution going on, which is related, at least in this model, is related to the possible solution of the CC problem. Okay, maybe you don't buy, and maybe it's just a way to convince yourself that it's so difficult that it's probably just an anthropic explanation. Okay, thank you.
Thanks a lot. Time for one question.
So very quickly, so yeah, so you are getting this lambda that you're saying, okay, well, this vacuum that maybe it's technically natural or something, but still, don't you still have the contribution, the usual contribution from matter to vacuum? I mean, the usual lambda. I mean, that's not what we can add, and then we see that part is not technically natural.
So what do you mean by?
I'm talking about
the standard?
the contribution of matter today to lambda, the vacuum energy that usually calculates.
You mean loops?
Yeah, exactly.
Yeah. I mean, let me stress again because this is an important point. So everything is taken into account in the following sense. During this phase. sorry, during this phase, I have a certain vacuum energy, dark energy, whatever. It includes, for example, all the loops of the standard model. It includes, I don't know, the QCD vacuum, okay, which is, as I said, this is a very low temperature phase, so it's in the same phase we are probing. So it contains everything that we, because everything, what is important is that everything you are saying contributes to the Hubble, and we are sensitive to Hubble back then. The second step, which is crucial, is that this vacuum energy is related by symmetry to the one we are observing today. Okay, so these are the two steps, and it includes everything. It includes because everything contributes to, yeah.
Thank you. So Andrew is the next speaker.